want to be there. I want to be here. All right. So this first one is about reflection. And let's watch this real quick.
Your eyes allow you to see the world around you. But have you ever wondered how they work? First, it's important to know that vision depends on your brain as much as on your eyes. Your eye's main job is to detect patterns of light. Then, they work with your brain to turn those patterns into images. Let's take a closer look. Light rays bounce off an object you are looking at. Let's say the object is a dog. The light reflects off the dog to your eye. Then, the light enters through the outer part of your eye, called the cornea. The cornea is clear like a window. It helps your eye focus the light to make things look sharp and clear. Next, the light rays pass through an opening called the pupil. The pupil is the dark round circle in the colored part of your eye. The colored part is called the iris. It controls how wide the pupil is and how much light can pass into your eye. In bright light, the iris narrows the pupil, reducing the amount of light that enters the eye. In dim light, the iris widens the pupil to let in more light. All of this happens automatically. Behind the iris is the lens of the eye. It helps focus the light coming into your eye so you can see things clearly. The lens flattens so you can see things that are far away, and bends so you can see things up close. When the lens, cornea, and pupil are all working together properly, they will focus light on the back of the eye. That's important because lining the back of the eye is the retina. There are about 130 million tiny cells in the retina that are sensitive to light. When these cells detect light, they turn it into electrical signals. Those signals eventually make their way through the optic nerve, which is like a cable connecting the retina to the brain. The retina helps create a rough image, but it sees the world upside down. It's your brain that turns what you see right side up. Also, when you look at an object, each eye gets a slightly different view of the world. The brain combines those views and makes them into one picture. The brain also adds a lot of details to your vision, so that you can see complex shapes, movement, depth, and a rainbow of colors. And of course, the brain connects your sense of sight to things you already know, so that when you see a dog, you recognize it as a dog, and not a cat or a monkey. And that's how you're able to see. To learn more about how your eyes work, visit nei.nih.gov/.
Okay, so the reason why I wanted to start with that was because I want you to make this connection between physics and biology. To understand that, you know, there's a lot of intersection here. Obviously, we did that with the physics of coronavirus, but I also want you to understand that, you know, when we talk about the STEM track, physics is offered in the STEM track, not just because it has to do with engineering, but it's the underpinnings of a lot of what we study in chemistry and biology and also in medicine. And so when you are you know, some of you want to be doctors, some of you want to go into the medical field. If that's something that you want, you really have to be good at physics. You really have to have a good understanding of a lot of these things, so that you understand how those light rays are entering the eye. If you wanted to be an optometrician, you would need to understand, hey, this is how light enters the eye. This is how the rays are being bent as they go through the lens, how they get focused on the retina, and so you can understand the whole system. So I just wanted to give you that link that, that we're not just talking about something that exists somewhat abstractly. So bottom line, without light, we don't have sight, okay? So we can't see anything without some light. In a black room, you can't see anything, right? There's no light coming in. And black, we refer to it as a color, but truly it is the absence of light, right? It's not anything special. It's just, if there's no light, then that's what we call black. And there actually is a color, you may have seen it. There's a couple good videos about it called Vanta Black, I think is what it's called. And it's the blackest black that exists. It is a specific kind of paint that apparently when you look at it in real life, your brain doesn't really know what to do with it because it absorbs all of this incoming light such that you your brain gets tricked into thinking that it's looking at something that can't exist, yet it does. Because even things that are black, they still reflect a little bit. And so we still see it. We can still make out the contours of the object. But this absorbs like 99.8% of the light rays that hit it.
How would you get it to reflect less?
That's a great question. So Vantablack is, I believe, made up of these little carbon nanotubes that trap the light inside of the little nanotubes and makes it bounce around inside of the little nanotube so that it can't escape. And so it just absorbs it. The consequence of that is that when you shine a light on the Vantablack, it actually warms up that object significantly because it's absorbing all of that radiation and trapping it really, really, really well. Good question.
Wow.
So definitely look it up. There was an artist, there was a really rich guy, I think he bought the patent on Vantablack, and everyone else in the art world, because he bought it and then he jacked up the price on it or wouldn't sell it to anyone, then there was this other guy in the art world who made the pinkest pink and gave it away for free to everyone except for this one guy. You had to prove that you were not the one guy who bought the blackest black, just to be a troll. And so it's this ongoing war between the pinkest pink guy and the blackest black guy. Not saying that the skin tone or race or anything has anything to do with it. It's just like two colors that apparently are going back and forth in the art world. Okay, so that being said, that's a fun tangent to go down. But when we talk about objects in this light world, right? We're talking about luminous and illuminated objects. Luminous objects can make their own light. Illuminated objects can reflect light. The simplest example of that is the sun and the moon. When the moon shines, is the moon making light?
No.
Right. Moon's not making light. Moon's just reflecting sunlight. When I was looking for pictures like this, I did find one where the moon appeared to be full and the sun was behind it. And I went, no, I'm not going to use that picture because it's astronomically incorrect. There's no way that happens. You wouldn't see on the same horizon a full moon and the sunset. When the moon is full, it is opposite the sun, meaning when the sun is setting, the moon is rising, and when the moon is setting, the sun is rising for a full moon. But it's a little bit of an exaggeration, but this is an astronomical possibility. You can see a crescent moon at the same time as seeing the sunset. It'd be very difficult. You'd have to have a really strong filter. But the moon does reflect the sunlight. That's the point here, all right? And so a common demonstration in physics in a classroom that we're not in right now, a common demonstration in physics is to shine a laser light and to shine a laser light off of a mirror. And when that laser light is shown off of a mirror, you don't see the path of the laser light through the air because it's not bouncing off of anything. Of course, if you sprinkle some dust, right, in there, then you might see the laser light reflect off the dust. And this is why you see in some movies where there's some security system and all the lasers are there. Then sometimes the protagonist, or the robber, the thief, whatever, dumps some substance, some dust or sand or whatever, in order to be able to reflect that laser light. Sometimes, for no good reason, you see the laser light crisscrossing the room. And that's false. That's not how laser light works. Laser light needs something to reflect off of in order to be able to see it. Okay, so for example, a medium like water is really good for us being able to see the laser light because it's reflecting off those molecules of the water. And in fact, there's a really cool phenomenon that happens at the top of the water, where the top of the water acts as a mirror. And so you see the laser light bouncing off the top of the water and going in the same angle that it hit it. And actually, that is a law that we're going to talk about, where the angle that the light hits a mirror is the same angle that it will reflect off of that mirror. Right? So if the laser light passes through fog, you're again going to be able to see it because it'll bounce off those molecules of water vapor. If the air is dusty, you'll be able to see it. But think about, you know, the spotlights that are shown and they reflect off the clouds, all right? And so then you're able to see it reflected off the clouds, that spotlight. If someone's trying to advertise something, or it's the bat signal, and you got to put on your costume, all right? So just understand that light needs something to reflect off of. That's where we're headed with this. Another thing to keep in mind is that in order to view an object, you must sight along the line at that object. It seems obvious, but you have to, light is not going to bend, not in the distances that we're talking about, right? Light does bend, but you have to be line of sight with an object in order to be able to see it. And when you do, light will come from that object to your eye along the line of sight. It's convenient to think about that line of sight as a cone, right? And your eye is capturing that cone of light coming from that object that is either reflecting or creating light. You have to be within line of sight. You know that if light is hidden behind a corner, you can see the reflected light, but you can't see the light directly. So that brings us to understanding what we mean when we talk about rays. You know, everyone kind of understands what a ray is because we talk about sun rays, right? An object illuminated by light in a room has a countless infinite number of rays reflecting off that object. It's not technically an infinite. You could probably figure out some way to count it, but it's effectively infinite. So there's a certain number of rays that reflect off that object. And we classify those rays in two ways. There are incident rays that are light rays that approach that surface. So if this is the floor, right? There's an incident ray that's coming from the overhead light that's hitting the floor and then reflecting off of the floor. The reflected ray is the light ray that reflects off a surface and eventually travels to your eye so you can see that ray. Okay, we don't see the incident rays, we see the reflected rays. We know the incident rays exist because in order for the reflected rays to exist, they had to initially be an incident ray that hit that surface. Now you see right here, what I was just talking about with the laser light is that this theta, this angle of incidence, is equal to this angle of reflection, meaning the angle between the perpendicular to the surface is equal to the angle perpendicular to the surface and between the perpendicular and the reflected ray. These two angles are equal to each other. That is a law. That is always the case for reflection. So, in order to determine, using this information about incident and reflected rays, to view an object in a mirror, what we can do is we can sight along the line at the image, and we'll know that one of the rays from the object will reflect along your line of sight. And what's interesting about this is that if this is a mirror, we will see an image. This is where the image will appear to be. It will appear to be behind the mirror and an equal distance away from the mirror that the object actually is. In other words, this distance here is exactly equal to this distance here. Right? This image doesn't actually exist. This is where we perceive the object to be. based on its reflection in the mirror. In other words, object distance equals image distance. Now I want to ask you real quick, for these three examples, and again, I'm looking at like 4 windows, which is why I'm having to move things out of the way while my mouse is moving all over the place. But I want to know why these 3 are wrong. So first of all, why is this one wrong? Why is this diagram of the object, the mirror, our eye, and the image, why is that incorrect? It's ridiculous, but I want someone to tell me why it's incorrect. Okay, the line is a spiral. So how does light move? Does light move in spirals or does light move in straight lines?
Straight lines.
Yeah. So this one is like light is taking, I don't know, a side trip to Detroit before it gets around to getting your eye. Doesn't make any sense. So yeah, just X that one right out. Like, just do that. Okay. How about this one? This is where we start having to use a little bit more of our knowledge here. This is the mirror. This is the incident ray, and this is the reflection ray. Why is this wrong? So if this is the incident ray, where should the reflection ray be going?
Directly back, like into the eye or whatever. Or no, sorry, I got the angle. It's like the equal angle on the opposite side, or whatever it is.
Yeah, equal angle on the opposite side. Awesome. And this object happens to be perpendicular from the mirror. So it's going to bounce straight back. So that's a 90-degree angle. 90 degrees, 90 degrees. All right, in order to meet the eye, and so let me be really clear about this. In order for that image to meet the eye, let's see, that looks about right. The ray incident from the object, the incident ray, has got to hit the mirror at an angle so that the reflection ray will bounce back to the eye at an equal angle from that perpendicular. So again, let me draw the perpendicular. I did a crappy job doing that. That is not where it should be. Let me move it. There we go. So I think I did a decent job here. The angle right here is equal to the angle right here. And so this incident ray bouncing off the mirror, creating this reflection ray that goes to the eye, that's how we see the object. We don't see the object because there's a light ray that goes perpendicular to the mirror and then bounces off in whatever direction. Right? The reflection is exactly the angle of incidence. Angle of incidence equals angle of reflection. All right, this one here. Why is that wrong? Where is that light ray going? Yeah, you got a messed up mirror. That light ray is going through the mirror. And secondly, it's bouncing off the image at an angle that it should not be bouncing off anything at, right? Well, mirror is glass, right? Mirrors are glass. Let's get that straight. But there's a silver backing to a mirror that creates the reflection. Okay, yes, that mirror is a window. And that's not how light rays work. Okay, so now that I think you've got an idea of why those are wrong, let me get rid of those. Here's where we formalize this, okay? So what we can see here, couple drawings. There is this normal line that is perpendicular to the mirror, all right? So that's what we're gonna call this now, this normal line that is perpendicular to the surface and divides the angle between the incident and reflected ray into two angles that we call the angle of incidence and the angle of reflection. These two angles are equal to each other, and that allows us to calculate where the object actually is based on where we see it. All right, so you do need to be familiar with normal line, angle of incidence, and angle of reflection. Questions about that? I'll just keep it on there then, just in case someone has a question. So now you should have all the information you need in order to be able to do, some of you, I know you're very productive and very efficient about how you work, that some of you already probably started this or were working on it while I was talking, which is not a bad thing to do. So you should have enough information to be able to answer all of these. Please do not hesitate to ask as you're working on this, and I will jump in and answer your questions.